All right, welcome back to the second video of the section. We've got a list of three vectors here, a1, a2, and a3, like so. That the list of the three vectors is essentially the same thing as this matrix. So when we have more than like vectors that aren't in R2, like more than two vectors in R3 or more, it gets a little bit more complicated. Like a lot of people can look at this and right off the bat, like from example one, see that one of those is a multiple of the other because you can see how they're proportional. But it gets more complicated than just being proportional when we're talking about R3 and above. So, fortunately, the concepts about pivot positions and row reduction and all that stuff work exactly the same in R3. So, first of all, we want to know, is the list of vectors linearly dependent or independent? So that's the question. Is there a non-zero solution of this vector equation? And we've seen a bunch of times by now, I'll skip the steps, that this vector equation is the same as the system of equations that looks like so. And that system of equations has an augmented matrix that looks like this. Okay, and you notice that the matrix A is the coefficient matrix of this system. But anyway, let's row reduce it. We have a -1 here, which is nice. So let's use that to clear away the 2 and the -1 below it. We're leaving row 1 alone. For row 2, we're doing 2 times row 1 plus row 2 to get zeros below this pivot position here. That's going to be a 0 here because we're doing 2 times -1 plus 2. 2 times -3 plus 5 is -1. 2 times 1 plus 2 is 4. 2 times 0 plus 0 is 0. Likewise, we're going to do -1 times row 1 plus row 3 to clear away that bottom left non-zero thing. So that's -1 minus 1 is 0. -3 minus 2 is 1. And -1 minus 1 is -2. And then -0 plus 0 is 0. Okay. Next we have a leftmost non-zero entry here, so that's going to end up being another pivot position. We can clear away what's below that by adding row 2 to row 3 and replacing row 3 with that result. So there we go. This is now in echelon form, so we can see where the pivots are going to be. We have one in every row of the matrix and also one in every column on the coefficient side of the matrix. So what does theorem 1.2 say about this? It says the system is consistent because the augmented matrix does not have a pivot in the rightmost column. And yeah, you can see if the rightmost column is all zeros, there's no way to have a pivot there. So yeah, it's definitely consistent. Homogeneous systems with zeros over here are always consistent. Do we have no non-pivot columns? Yes, we have no non-pivot columns. So the solution is unique. And we also know that the vector 0 is a solution because, of course, you could do 0a1 plus 0a2 plus 0a3, and of course you'll get 0. So the unique solution is specifically x equals 0. And if there's only that unique solution, the trivial solution, it's trivial because it's not interesting, right? Trivial stuff means stuff that like you don't have to worry thinking about. Like it's always a solution. That means the list of vectors is linearly independent. Okay, let's look at part B. Yeah, if you notice my microphone sounds different, it's because I just realized I did a bunch more work, but I wasn't actually recording, and then I tried messing with microphone settings, so maybe it sounds better now. Anyways, let's do part B. First time for you, second time for me. That's okay. I like linear algebra. I don't mind. It's fine. So B says, can you write the null space of A as the span of some vectors? Well, uh, the definition of the null space of A, it's the solution set of this, and we just talked about the solution set of the homogeneous equation, and we found that the only solution is 0, the trivial solution, x equals 0. So we can write that solution set as just like the set of one vector. That's what this notation means. And we want to know, can we write that as the span of some vectors? Well, I guess, okay, it would just be like just this one point right here. That one point is the null space of A, just the 0 vector. Well, what if we think about it as the span of the 0 vector? Is that the same thing as just the 0 vector? Well, the definition of span, it's the set of all linear combinations, or in this case, just the set of all scalar multiples of 0. So it doesn't matter what the scalar multiple is, what the coefficient is, because any coefficient times 0 is 0. So this is just the set 0, which is equal to the null space, like we just showed. So yeah, we can write the null space of A as just the span of the vector 0. Okay, what about part C? Can you write one of the columns as a linear combination of the preceding columns? So this is sort of a weird question because, well, it's like, which column are we talking about? There's 3 different columns. Well, A1 has no preceding columns. There are no columns before it. So that one's definitely going to be no. But we could ask the question, can you write A2 as a linear combination of A1, the column before it? So that's one question we could ask. And another question we could ask is, can you write the third column as a linear combination of the 2 preceding columns? So is there some x1 and x2 so that you can get a linear combination of A1 and A2 to get A3? So let's think about these 2 questions independently. If the first question is yes, then let's think about, what does that say about the linear independence we just showed? How does this equation relate to the homogeneous equation we just looked at? So if there is an x1 that makes this true, could we write 0, like get 0 on one side of it? Sure, we could subtract a2 from both sides and we'd have the homogeneous equation. Right? Just subtracting a2 from both sides gives you this. And I just wrote the 0, a3, just for fun, or just to show that this would make the point x1, -1, 0, a non-trivial solution of the homogeneous equation. And we just showed there isn't one. The reason we know this is non-trivial is because of the fact that that -1 is not 0. So the answer to this is no, for the reasons we just showed down below. And the same idea is going to be true with the second equation. If there is an x1 and x2 that gives you a3, so just like before, if you have an x2 and x1 that makes this equation work, you could just subtract a3 from both sides to give you x1a1 plus x2a2 minus 1a3, which is a non-trivial solution of the homogeneous equation, which does not exist because the set of vectors is linearly independent. So it turns out, in general, B and C are equivalent for any matrix A, which we're sort of going to show it with some examples like this. What about part D? Is the span of A1, A2, A3 equal to R3? We know every linear combination of A1, A2, A3 is definitely an R3 vector because we're, combining these R3 vectors together to get another R3 vector. But is every R3 vector also in the span? Can every R3 vector be written as a linear combination of A1, A2, A3? In other words, no matter what vector y you have, does the following vector equation have a solution? Because this equation having a solution, the solution means the scalar coefficients that make it so you can get that linear combination equal to your vector y, no matter what that vector y in R3 is. If the answer to that is yes, then the span of A1, A2 equals R3. It's like any vector in R3, any y in R3 can be written like this, as something in the span. So we've shown before a bunch of times why this vector equation is equivalent to the system of equations with the following coefficient matrix. Now, what we should probably do here is row reduce this to see, does this have a solution no matter what y is? But we've actually already row reduced it, sort of. We row reduced the corresponding homogeneous equation over here, but now it's a little bit more complicated because when we do like the multiplicity operations, we have to keep track of the multiples of the y's. Or do we? Maybe we can just like not and say we did, because I know what's going to happen to the coefficients. The coefficients are going to come out to be the same thing they did here once we get it into row echelon form. But I don't know. There's some stuff over here. Who knows what that is? Now, Do we actually have to find the solution? The question doesn't say find the solution in terms of y. It just says, does it have a solution? And fortunately, because we've been studying theorem 1.2, we know that this is always going to have a solution because we can see where the pivot positions are. Is there any way there could be a pivot position in the rightmost column when it's in echelon form and all the leading entries are on the left? No. There's no room for a pivot in the rightmost column, no matter what the y values are, because all the pivots are on the left. So theorem 1.2, part 1, says that this is consistent. No matter what the vector y is. And what does that mean? That means that the span of A1, A2, and A3 equals R. 3. All right. So the next two examples are the same idea as this. Maybe we can skip some of the steps, well, especially because there isn't enough room to write everything. Let's look at example 3 next. Here we have a list of one vector, just A1. Is that linearly dependent or independent? So the question, if it's dependent, is does x1a1 equals 0 have a non-trivial solution? And again, the non-trivial solution that we're talking about is the coefficient x1. Well, this equation would just look like negative 3x1, 0, x1 equals 0, 0. And just the first part of this says you'd have to have negative 3x1 equals 0, which you know from algebra that means that x1 must be 0. So that means it's only the trivial solution, which means it is linearly independent. Can you write the null space of A as the span of some vectors? Okay, well, the null space of A is just the one solution, the trivial solution. And this is just like part B before, just like what we did here. It's just the 0 vector. But in this case, it's really just the 0 number. And you can think of that as the set of all multiples of 0. So yeah, if you want to write this as a vector or not, it doesn't really matter. So yes. Does A1 span R2? Spanning R2 means everything in R2 can be written as a linear combination of A1. Okay, here's negative 3, 0 over here. Here's that vector. And the span of A1 is just going to be the whole x1 axis. All that stuff. And that doesn't get you everywhere in R2. So there are lots of R2 points over here and here and here and here and here that are not in the span of A1. So the answer to the question, does it span R2? No, it just spans the x1 axis. Okay, so that one was a little easier. This is sort of a special case when you just have a single vector. And when you have a single vector, and that vector is non-zero, that was kind of important here. The only way you're going to get 0 as a multiple of this non-zero vector is when the scalar multiple is the trivial solution. So that sort of shows why theorem 1.4 is true. If a list contains only a single vector, and that vector is not the 0 vector, then that list is linearly independent. All right, let's look at example 4. Oh, maybe you got a sneak peek at theorem 1.5, and that's going to tell you the answer to this. But we don't want to use that theorem because we're trying to justify the theorem with this example. So we have a list of two vectors that form the columns of this matrix. Is that list of vectors linearly dependent or independent? Let's see. So I'm going to ask a question in the form, is it dependent? Does this homogeneous equation have a non-trivial solution? Can you think of a way to get an x1 and an x2 to make this come out to 0? I'll let you think about it for a minute if you want to pause the video. And the answer is yes. X1 can be anything. For example, the square root of pi. But x2 actually has to be 0. Right, because we're going to do the square root of pi times 0 and 0 times 3, and that will be 0, and the square root of pi times 0 and 0 times 2, and that adds up to 0 as well. So, yeah. So that answers that question. We have a non-trivial solution here. Non-trivial because the square root of pi is not 0. Okay. That's A. Can you write the null space as the span of some vectors? Okay, well, maybe we actually do need to go through the work of solving it now. I'm going to do this on the side because we might run out of room. So I'll skip the steps that we've already done a few times, but we're talking about the system of equations with the following augmented matrix. We have our coefficient columns here. We want to know what are the x1 and x2s that make this true. We can row reduce this by multiplying the top row by 1/3. And then you can do -2 times row 1 plus the second row to clear that away. And everything else is just like 0 plus some multiple of 0. So that's what you get. And this is now in reduced echelon form, reduced row echelon form. And we have a non-pivot column. The non-pivot column is the x1 column. That's why x1 was free to be anything you want, like the square root of pi. So we can write let's just write the system of equations here. This says x2 equals 0 and 0 equals 0, just directly translating this. But if we want to write the solution set of this as the span of some vectors, we need to write all of the variables in terms of the free variables. So x1 is just equal to x1. That's the free variable column that we had. And x2 has to be 0. So we can say that this as a vector, the set of all vectors that can be written like this, because x1 can be any real number. We can think of this as x1 multiplying 1, 0. So the null space is the set of all vectors that can be written like this for any real number, x1. And that is the same thing as the span of 1, 0. Cool beans. So that's part B. Let's look at part C. Can you write column 2 as a scalar multiple of column 1? Well, let's write that out. So is there a scalar multiple of column 1 that gets you column 2, which is the vector 3, 2? No, there's no way to multiply x1 by 0 to get either 3 or 2. Does the list A1, A2 span R2? Well, Is every vector in R2 in the span? This is an R2, so it's not too hard to just draw the span of these. So here's the A1 vector right at the origin. A2 is 3, 2. It's out here. So when we get any multiple of 0, if we try to stretch out that A1 vector, it's not going to go anywhere. But we can stretch out the A2 vector and get other points over here if we make it longer, or we could multiply A2 by a negative number and get points out here. And then you could add plus 0 to those if you want, or not. But that gives you the span of A1, A2. It's just that line, and it's not all of R2. R2 includes points out here, and out here that cannot be written as a linear combination of A1 and A2. So the answer to the question is no, it does not span R2. Okay, so these examples that we've done here are sort of to give you an idea about how these questions can be kind of complicated, and they're also related to each other, but there are some situations where it's kind of simple. Like if you have a list of vectors that contains the 0 vector, then that is automatically going to be linearly dependent, because we basically saw that you can multiply that 0 vector by any non-zero number you want and get a non-trivial solution to the homogeneous equation. And theorem 1.4, we already talked about how example 3 kind of illustrates why that is true. So yeah, let's actually just do example 5 here, and then we'll take a break because this has already been a long video. So hopefully you've already done the stuff about basic proof writing, which talks about converses and counterexamples, but let's just go through it really quick. Both of these statements are like of the form if P, then Q, right? If P, then Q. And really most math theorems tend to be written like that. Now, we know it's false if there exists a counterexample. Now, these theorems do not have counterexamples because they are true. I wouldn't call them theorems if they were not always true. So a counterexample makes it so P is true and Q is false. So like if it were possible to find a list of vectors that contains a 0 vector but is not linearly dependent, that would make theorem 1.5 false. And trying to think of counterexamples is a good way to understand why theorems are true as well, because if you try to think of a counterexample and you can't, you're gonna understand something about why there are no counterexamples and why the theorem is true. Anyways, the converse of an if P then Q statement is when you switch the order of them. And if both are true, we would write P if and only if Q, or abbreviate it as P if Q. That means if and only if. So now, if the converse of these theorems 1.4 and 1.5 were true, we probably would have just written the whole if and only if statement as a theorem. So that's another way you can understand a theorem, is by trying to find a counterexample to the converse, just to understand the mathematical space around the theorem to get a better picture of what is true and what is not true here. So here's an example. The statement if x squared equals 9, then x equals 3 is false because there's a counterexample. Like, can you think of how to make x squared equals 9 be true, but make q, which is x equals 3, false? Yeah, that would be x equals negative 3. The converse of this would be true. If we said if x equals 3, then x squared equals 9, that would be fine. All right, so let's think about the converse of theorem 1.5. We're going to switch the order of the P and Q. So the converse is if a list is linearly dependent, then it contains the 0 vector. Well, good place to pause and think about it. Can you think of a list that is linearly dependent, but it is not true that it contains a 0 vector? Sure. We need to make it so, I don't know, it's good to think of our two examples. We want to make x1 times something plus x2 times something else equal the 0 vector, but we don't want either of these vectors to be 0. Okay, what if we just make them like opposites of each other? Like 7, 3, and -7, 3. Then sure, we can do 1 times the first one plus 1 times the second one. Sorry, -7, -3. And that will give you 0. So this list is linearly dependent because we have a non-trivial solution to this homogeneous equation, but the list of vectors does not contain 0. So yeah, is the converse of theorem 1.5 true? No. Here's a counterexample. Okay, now is actually the time. This is already a long video, I know, but now is actually the time to talk a little bit about the strategy to write the null space of a matrix as a span. We already used this in examples 1 through example 4, just to show you what we did. We take the homogeneous equation and write it as an augmented matrix, reduce it to echelon form, and solve for all the variables in terms of the free variables. And you know when you do that, because it's homogeneous, you're not going to have any constant coefficients over here. And that means that any solution of the homogeneous system can be written as a linear combination of some vectors with the free variables as weights. So the solution set is the span of these vectors. That's what we did over here. With B, we solved for all the vectors, we solved for all the variables in terms of x1, and we can write any solution as a linear combination of these vectors with x1 as a weight, so that gives you the span of that vector. If the vectors are linearly independent, it means that the only solution is the trivial solution, and you can just write the trivial solution as the span of the 0 vector like we did over here. So it's always possible to write the null space as a span. In example 1 here, we solved for x1 and x2 in terms of x2, and that gives you, because there's no other constant coefficients here, right? This was just like 0, 0 because it was homogeneous. We can write any solution as a multiple of that -4/3, which gives you the span of that vector. Okay, so that's what that says. This is going to be a thing we use a lot, like writing a null space as a span of some vectors is something that we'll do a fair amount throughout the class, including later on in chapters 5 and 6 and 7. Okay, so let's take a break, have a drink of water, take a nap if you need it, come back fresh, and try to do more of the section. Take care.